I'm a fifth-year PhD student advised by Professor Anand Lewis. I'll be chairing the session today, and my colleague Atasi will be chairing the session tomorrow. Over the next two sessions, we'll explore the fascinating intersection of modern algorithms and machine learning. We have an incredible lineup of speakers for the next two sessions. Together, they'll cover topics ranging from sketching and streaming algorithms to Corsets and the theoretical limitations of graph neural networks. We extend our gratitude to the Walmart Center for Tech Excellence for their support, and to our organizers, Professor Arinam Khan and Professor Anand Lewis, for making this event possible. We hope you enjoy the sessions, and let's get started. So first we have Professor David Woodruff speaking. He's a professor in the computer science department at Carnegie Mellon University. Prior to joining CMU, he spent a decade as a research scientist at IBM Almaden Research Center, where he was recognized as a master inventor and a member of IBM Academy of Technology. David earned his PhD from MIT in 2007 and is renowned for his contributions to data stream algorithms, distributed algorithms, machine learning, numerical linear algebra, optimization, sketching, and sparse recovery. His groundbreaking work has been recognized with numerous prestigious honors, including the 2020 Simons Investigator Award, several Best Paper Awards at conferences such as Stock, Pods, and most recently he received the Stock 2023 Test of Time Award for his lasting contributions to the field. So we are happy to welcome David. Over to you.
Thanks very much for the introduction and for coming. So today I'm going to talk about an overview of dimensionality reduction methods. So here's the outline. I'm going to introduce dimensionality reduction or sketching by looking at two classical problems in machine learning. One is regression and one is low-rank approximation. We'll see how to use sketching to get fast algorithms for these problems. And then we'll see variations of it, so how to guarantee things like high precision, or in the context of low-rank approximation, how to get your low-rank factors to be actual column subsets, and so on. So this is the outline. Let's start with regression. So this is one of the simplest and oldest models in machine learning. Suppose as input you're given n by d matrix A and a vector B. So think of having n examples, one for each row, and the columns are the features, and the entries of B are the labels. And you want to find a vector x and r to the d. So this is the equation of a hyperplane that minimizes the squared Euclidean distance between what you predict, which is a times x for each of the n examples, versus what you observe, which is each of the entries of B. Yeah, this is a simple model. There's a nice closed form solution for regression when A has full column rank. If it doesn't have full column rank, there's still a nice closed form solution in terms of the pseudo-inverse. The issue with this is that computing this closed form solution is slow, so naively this takes n times d squared time. It's slow if n is large, d is moderate. And an actual question is, can we speed this up with some kind of dimensionality reduction, or by using randomization and sketching? So here is a simple example of what I like to call the sketch and solve paradigm. So first we relax the problem. Instead of solving for the optimal solution x star, we allow ourselves to output a solution x prime for which the cost of using x prime is at most 1 plus epsilon times the optimal cost, and we allow some tiny probability of failure. Okay, so the basic idea behind this framework is we're going to choose a random matrix S. This is called the sketching matrix. This random matrix is very wide and fat. Okay, so it's k by n, where k is much less than n. Okay, many fewer rows than columns. And what you do is you take your matrix A in regression, this n by d matrix, and you squash it down to a k by d matrix, S times A. Okay? by computing this matrix-matrix product. Similarly, you replace B with S times B. It's now a k-dimensional vector. And now you simply solve this much smaller version of the same problem. You try to find the solution x prime to minimizing the norm of SAX minus SB. Okay, the matrix A is S, has been replaced with SA, the vector B with SB. You solve this, you get a d-dimensional vector x prime, and you plug it back into the original regression cost, and the hope is if you've chosen S appropriately, then you do get a good approximation with good probability. Okay, so that's the basic idea. There are lots of design choices here. Which families of random matrices S should I choose? How many rows should I choose? And so on. Any questions? Okay. Yeah, so we want our solution x prime in the smaller so-called sketch space to be a good solution in the original space. So what kind of sketching matrix should we choose? One of the most natural families that might come to mind is a matrix, a Gaussian matrix. Okay, so a matrix of IID normal random variables. And in fact, if you do this, it works. And the number of rows is, so you can choose d over epsilon squared rows will suffice here. In fact, you can get d over epsilon rows using normal random variables. But one of the main issues here is that although this has a nice small number of rows, which in fact is optimal, computing S times A is slow, right? So you have this matrix that's dense, a dense matrix of normal random variables, and so it's going to take you at least nd squared time to compute S times A. So doing the dimensionality reduction itself is slow. And in fact, the closed form solution for regression can be computed in nd squared times. So not only are you slower, but you're not as accurate anymore. But it turns out that you can instead choose S from a much more structured random family of matrices. So you can choose so-called subsampled randomized Hadamard transforms. This was initially observed by Sarlos. What are these things? So these matrices can be factored into the product of three matrices, P, H, and D. I can draw this. So D is just a diagonal matrix, which has plus minus 1.
So David, I think this side will be better.
Did that side will be better?
Yeah, I think that is.
Okay.
The camera will cover.
Camera can see me. Okay. So D is diagonal, and each diagonal entry is independently plus 1 with probability a half and minus 1 with probability a half. Okay. This is D. H is the n by n Hadamard matrix. And so the entries here are plus minus 1, and I'm actually going to normalize them by root n. The ijth entry of H has a closed form expression. It's 1 over root n times negative 1 to the I dot j. So here I and j are interpreted as vectors of length log n. So you can think of these as binary vectors of length log n. You take your dot product. Anyway, this is just an explicit description of this matrix H. There's no randomness here. It's a deterministic matrix. And finally, so you actually haven't reduced any dimension. This is n by n, this is n by n. And finally, P just randomly chooses a small set of rows of H times D. Okay, so for each row, there's a single non-zero entry in a random location. And that's just sampling a row. Okay, so this is where you get your dimensionality reduction. And you can see that computing S, which is P times H times D, is fast because this is a diagonal matrix, can be applied very quickly. H actually has a nice recursive formula, so an n by n Hadamard matrix can be written recursively. So let me just write Hadamard, that's n by n, is can be written as a block matrix in terms of n over 2 by n over 2 Hadamard matrices. And because of this, you can do a divide and conquer approach to quickly apply h to a vector. And finally, this is just random sampling coordinates of a vector when applied to a vector. So you can see p times h times d is fast. And the intuition of why it works, well, some basic property you would want of these projections is that they preserve norms of a vector. You can see that scaling entries by plus minus 1 will preserve the norm. H is actually an orthogonal matrix, so it preserves the norm, orthogonal matrix. And this is a sampling matrix. And you might be concerned that if I have a vector and I just sample some of the coordinates, I might miss important coordinates. So I just uniformly sample. What if there's some large coordinate? And the point of HD is it's kind of a cheap rotation, so it spreads the mass across all the coordinates so that uniform sampling is then effective. Okay, so that's the idea behind this. Yeah, so I just explained this. Has roughly the same number of rows as a Gaussian sketch. And the important thing is that actually, if you work it out, S times A and S times B can be computed in nd log n times. Okay, so much faster than the earlier nd squared. Okay, and yeah. So once you compute SA and SB, you can then solve regression on this small problem with this additive poly d over epsilon term. There's actually poly d log n over epsilon. Okay, any questions? Good. Okay, so that's great. It's nd time, which is the time to read the matrix A. But oftentimes, your matrix A might be sparse. And so you might want running time which is proportional to the sparsity of your matrix. And what you can do for that is you can use the count sketch matrix, which originated in data streams. So the idea is to choose a different random family of matrices S, which is, again, wide and fat, k by n. The number k of rows is slightly larger than before. So instead of being d, it's roughly d squared. But importantly, S is very sparse. So it just has a single non-zero entry in each column. So S just looks like this. It's k by n. And on each column, I randomly choose the location of a single non-zero entry. On that location, with probably a half, I put 1. With probably a half, I put minus 1. And I do that independently for each of the n columns, okay? So that's how you create this matrix. It's extremely sparse. Yeah, so that's an example of count sketch. You can think of it as hashing rows into k buckets, okay? So if I were to apply this to a vector, and I look at the first coordinate of the vector, then when you do this multiplication, you can think of taking the first column here, outer product the first entry, plus the second column, outer product the second entry. So this entry is just going to touch the single non-zero location in the first column. Okay, so if this is in some location I, you can think of listing all the hash buckets, 1, 2, listing a bunch of hash buckets, k, and somewhere there's the ith one, and x1 is going to hash to the ith bucket and get scaled by plus or minus 1, depending on, x1, depending if the sign is 1 or minus 1. Okay, and so you're just hashing coordinates into buckets and rescaling by plus minus 1. And when you apply it to a matrix, you're hashing rows and rescaling them by plus minus 1. So the key property here is S times A is computable in, if I apply it to a single vector, I only have to look at the non-zero entries in that vector. And since we said this is hashing, it just takes constant time per non-zero entry to update the hash buckets. So applying it to a matrix, which is just d columns, d vectors, I get n and z a total time, where n and z is number of non-zero entries. Okay, and you can prove that this works. I'm not going to do that here, but combining this with regression, you get NNZ of A plus poly D over epsilon times to solve regression. And that is optimal for relative error. If you don't read a constant fraction of the non-zero entries, you can easily get fooled to be missing some large entry, for example. Okay, so that's classic sketching for regression. Yeah, so the guarantee of these is that when you plug back x prime, you get a 1 plus epsilon approximation. Sometimes you're interested in other guarantees. So this is closeness in objective function value. But sometimes you might want your actual solution x prime that you output to be close to the actual optimal solution x star. You can translate these guarantees fairly easily. So let me just do the first one there. So if I look at x star minus x prime, and I know that if I were to multiply this by the minimum singular value of A, or the squared minimum singular value, then this would be less than A times x star minus x prime. Right? Because this is some vector I'm applying A to, so it's at least the min singular values of that matrix times that vector, right? Now what do I know about this quantity? Well, I know from the Pythagorean theorem, if I'm going to look at the cost of ax prime minus b for some x prime, I can decompose that, right? So you can think of this as having some vector b. Here's the column span of A. And the closest point is the solution. So this would be ax star. And if I want to look at, here's the orthogonal distance to B. If I want to look at some ax prime, which is maybe over here, then I have the Pythagorean theorem here, right? So I have that this square distance is what's up here, ax prime minus ax, let me write it like this, ax star minus ax prime squared, plus the distance to the optimum solution, which is ax star minus b2 squared. Yeah? It's Pythagorean theorem. And now we also know from closeness in objective that I can subtract ax star minus b 2 norm squared from both sides. And this thing is at most 1 plus epsilon times ax star minus b, right? So if I subtract this from here, then I get that actually I can upper bound this term as epsilon times the optimal cost. Okay, so if I divide by sigma min squared, I actually get the bound that's here. Okay, so I get some closeness of the actual solutions from closeness in objective function value. That's good. Okay. Now, you can actually improve this. So if you look at, you might think that maybe x star minus x prime is kind of, so you're bounding the 2 norm, but maybe you could say that on all coordinates x star and x prime are close. So that's what the infinity norm would do. It'd say the max difference between these two, between any coordinate of these two is small. And you can actually get that for the subsample randomized Hadamard transform. You can't get it for count sketch, but for that transform you can get that actually the max square distance across any coordinate is at most a constant times the average square distance. So that means I get to divide this quantity by d. Does that make sense? Okay. Another thing that you might want that we haven't seen so far is that if you want very high accuracy solutions, these are giving you polynomial in 1 over epsilon dependence. Yeah.
Just one quick. If I'm assuming that the optimum is sparse, does that mean it gets even better for SR?
Yeah, so if your optimal solution is sparse, no, I mean, it's not that it gets better, it's just that, if this is like E1 then this would have one coordinate which is very close to E1 and everything else is 0, all these other coordinates would be very close to 0. You would still have this guarantee, it's just that it's also very close to being sparse.
I meant for the other one, like just the distance. Does that get better if it's sparse then? Because it seems like that you're dividing by d, but you're only adding it up for maybe k-ish or something? I'm not sure.
Oh, I think it's possible to have an actual sparse optimal solution, but a non-sparse.
Approximate.
Yeah.
Okay.
Yeah. Yeah, I think there should be a simple example, but yeah, I have to think about it. Okay, so another thing that you might want here, yeah, so these are poly 1 over epsilon dependence, but sometimes you want super high accuracy. Can you get a logarithmic dependence in epsilon? And there's a simple way, a less black box way of using sketching to achieve that. Instead, I can choose an S with an accuracy parameter which is a half. Okay, so then there's no epsilon, and I can solve for a 1 plus 1/2 approximate solution. So that's my solution x prime, and I'm going to call that an initial solution x0, because what I'm going to do is I'm going to use that solution to start an iterative method. I'm going to start running gradient descent actually from that solution. Now, if you're familiar with gradient descent, you know that the number of iterations depends on properties of your matrix. In particular, one of the main properties is the condition number of your matrix. So we can also use sketching to precondition our matrix. So what does that mean? So the condition number of a matrix, for our purposes, is the max singular value over the min singular value. And so this could be very bad. So the idea is, is there some way I can find a d by d change of basis, not an orthogonal change of basis, but a change of basis, so that, let me call it, I'm going to call the d by d change of basis R inverse. Is there some way I can find this so that this condition number is small? So maybe is order 1. Okay. There always exists a change of basis that preserves the column span and makes the condition number 1, because what you can do is you can take any matrix A and write it in its singular value decomposition, U sigma V transpose, and if I multiply by sigma V transpose inverse, so if this is my R inverse, then you see that these cancel and I just get an orthonormal basis. And so that has perfect condition number. It preserves the norm of all vectors. Now the issue with finding this is that it's slow to compute the singular value decomposition. So is there some way you can use sketching to get a quick and cheap preconditioner? And there is. So the idea is I'm going to compute my sketch S times A, and say with some with accuracy epsilon is a half. Okay, so the number of rows here is very small. It's poly D. And if I'm using count sketch, the number of rows here would be d squared. Independent of n is the important point. So I compute this matrix, which is d squared by d. And then what do I do? Well, why don't I compute the singular value decomposition of this matrix, which is much, much smaller? So I can write this matrix as, let me call it U sub SA sigma sub SA V sub SA transpose, okay, to indicate that it's the SVD of this small matrix. And now let's take this part here and let's call let's let R inverse be the inverse of this thing. So sigma SA V SA transpose inverse. Okay, so it's just like before. Before we said compute the SVD of the original matrix, and then you can let R inverse be this the inverse of this d by d part. And we know that if you multiply A times R inverse, you get a perfectly conditioned matrix. now I'm saying that's too slow. Instead, first sketch, compute the SVD of the sketch, define R inverse to be this d by d inverse from the sketch SVD. And now what do you think we do? We take this and we multiply A by it. Okay, by this thing. And you can show actually the condition number of this is at most 1 plus epsilon 0 over 1 minus epsilon 0, where epsilon 0 was the epsilon you use for this subspace embedding. Okay, so in this case it would be 3/2 over 1/2. That's 3. Do you want me to prove that? It's fast, but I don't know if I should skip proofs. This is a tutorial, but I'll prove it. It's easy too. So if I'm looking at the condition number of AR inverse, well, one thing I need to know is the sup over unit x of this, right? This is the max singular value, right? But the nice thing is, since I have a subspace embedding, I can say that this thing is the same as SAR inverse x, up to a 1 plus. So this is at most the sup over unit x of SAR inverse x. And not exactly, it's divided by 1 minus epsilon 0, right? Because it's a 1 minus epsilon 0 something. Now what is this norm? This one's easy. Well, this is just 1, right? Because how did we get R inverse? We took it from the SVD of SA. So when I multiply by R inverse, it cancels the R, I just get an orthonormal matrix. So this thing up here is 1. So this is 1 over 1 minus epsilon 0. Okay, and if you do the same thing for the the inf over unit x, and again use the subspace embedding property, you'll get that this is at least what is it? This is okay. Let's do it. AR inverse x, and this is at least. Oh, sorry. 1 plus epsilon 0. This is at least the inf over unit x of SR inverse x. And so this whole thing, this is a unit vector, so this is at least 1 plus epsilon 0. And finally, what is the condition number? It's the ratio of this to this. Okay, so yeah, that's why you get 3 if I did that right. Oh, sorry. This is what is it?
It's 1 on the right.
1 on the.
Plus epsilon is 1.
This is 1, right?
Yes. So you wrote that as
Yeah, I
it
do.
was 1.
So this should be 1 plus. Oh, I see. So this should be 1 over 1 plus epsilon 0. Okay, good. Thank you. So this is yeah. When I take the ratio of these, I get 1 plus epsilon 0 over 1 minus epsilon 0, which is 3. Okay, good. So yeah, that's a simple way of applying sketching to get a preconditioner. So you kind of shifted all the expensive stuff into the sketch space, which is very low dimensional, like poly D size. Yeah, and now if you run gradient descent on this precondition matrix, AR inverse, you never have to compute AR inverse, because when you do gradient descent, you always multiply it by some iterate. So you first multiply R inverse times the iterate, that's a vector, then A times that vector. So you don't have to do this matrix product. Do gradient descent with log 1 over epsilon iterations starting at your initial solution, also found with sketching. And that actually works. So preconditioning and the initial solution didn't actually depend on the real epsilon. It's just number of non-zero entries of A plus poly D time, and then log 1 over epsilon iterations of gradient descent, and each one is also n and z of A plus poly D time. Is it clear? Good? Okay. Okay. So There are other variants of regression for which sketching is helpful for. So one thing that people sometimes look at is ridge regression. So here you add a regularization term. So it's lambda times the square norm of x, where lambda is positive. This helps for various reasons. Helps avoid, finding an x that overfits your examples. Sketching here is useful both when the number of examples is larger than the dimension, and also when the dimension is very large. And one nice thing here is that the sketch dimension depends on what's called the statistical dimension of A, which is the sum over all the singular values I of sigma I squared over lambda plus sigma I squared. So when lambda is 0, this is just the rank of A. And that's what we said before. D was the number of rows. But if lambda is very large, this, as is often the case in practice, this can be much less than the rank. Okay, sometimes the statistical dimension is a constant. So you can replace your original ridge regression problem with the sketch ridge regression problem. Sorry, there should be an SB here too. And now the number of rows is only statistical dimension. But that's the usual way when n is much larger than d. But actually you can also sketch on the right here and reduce d. And the sketching dimension again depends on the statistical dimension, but also some other properties. So the max singular value of A compared to lambda. And you can do both sketches at the same time as well. This is related to some quantum-inspired methods. There's a lot of quantum-inspired work that looks at ridge regression. And some of the techniques in randomized linear algebra can be used to improve the bounds obtained in other ways. So let me also mention other loss functions. So least squares is quite good for Gaussian noise. But other loss functions are used for other kinds of noise. So you can look at L1 loss. You can look at what's called Huber loss, which is quadratic near the origin, but in a smooth way at some threshold becomes linear. Okay, so this is useful for dealing with Gaussian noise near the origin, but also useful for dealing with outliers as you move away from the origin, because you penalize them less since you're not squaring. There's also an extreme version of that, which is the Tukey loss, which is quadratic near the origin, and at some point it just is completely flat for outliers. And here you can imagine, outputting an x star that minimizes the m function loss of ax minus b, where m is a so-called m estimator. Each of these could be an example of that. So you're applying it coordinate-wise to ax minus b, and you're taking the sum. And there's a bunch of work on this that can reduce a big problem with respect to one of these arbitrary loss functions to a small reweighted problem, and the time it takes to do that is proportional to the number of non-zero entries of the matrix. Let me also say a little bit about what's called kernel regression. Actually, how much time do I have? 15 minutes? Okay, yeah. Let me say a little about kernel regression. So here you, where did I put the eraser? Oh. So kernels are popular in machine learning, right? Like if you, suppose you have some 4 points here as a classic example, and you want to draw a line that separates them, you can't really separate the x's from the o's, so instead you think of lifting the x's to a new dimension and separating them with a hyperplane. Okay, so you want to, you're given n points, x1 through xn, and you want to apply a nonlinear mapping phi to lift them to the so-called feature space. An example is the polynomial kernel of degree q. Here there's a nice explicit expression for the feature map phi. So I take a point x and r to the d, and I map it to a point in r to the d to the q. Q is the degree of the polynomial kernel. And I index the coordinates in the feature space by q tuples, each an index of d possible values. And phi x of I1 through IQ is just the product xi1 through xiq. Okay, and these are useful. Once you have polynomials, you can do Taylor approximations of other kernels like the Gaussian kernel and approximate them this way. So it's nice to have sketches for these kinds of feature mappings. And there's what's called kernel regression, which is the following. So we can define a matrix A in which is d to the q by n. So it has n columns, one for each of these points, and it has d to the q dimensions. You'd never want to write this matrix down, okay? Because d to the q is super large. So the ith column is 5xi. And the kernel ridge regression problem says find this n-dimensional vector y. So it's pretty small. You can think of n as smaller than d to the q. To minimize A transpose AY minus B 2 norm squared plus a ridge regularization. So you could try to solve this exactly. You'd have to multiply A transpose A. That's bad, but it's not as bad as actually forming A and multiplying A transpose A. You can use the so-called kernel trick because what you need is dot products of columns, two different columns of A with themselves. And actually the dot product of two columns of A is actually the dot product of the corresponding 2 points raised to the qth power. You can show that. So that's the so-called kernel trick to compute this quickly. But it would still take n squared d time to form this matrix and then solve the regression problem, which is too slow if n is large. So you can use sketches for polynomial kernels. So the first sketch was Tensor sketch due to Peg and Pham. This applies more generally when I'm tensoring q different vectors. On the previous example, in polynomial kernel, I'm tensoring one vector with itself q times. But I might want to sketch a d to the q dimensional vector, which is just a tensor product of q vectors. And the way you can do this is you can sketch each of the individual vectors. Okay, so with, say, count sketch 1 is S1, count sketch 2 is S2, and so on. And there's a way of actually thinking of the coordinates of each si, xi. You can think of these as coefficients of a formal degree k minus 1 polynomial in some variable z. So if I have k rows here, I just think of the first entry as the constant term of a polynomial, the second entry as the coefficient multiplying z, the third entry as a coefficient multiplying by z squared. I can think of this as a polynomial. It's kind of weird. And I have a bunch q polynomials. I multiply them all mod some other polynomial, z to the k minus 1, so that I still have a polynomial of degree at most k minus 1. I can do the multiplication efficiently using fast Fourier transform. Anyway, the point is, if you do this weird algebraic operation, this actually corresponds to implicitly applying a count sketch matrix S on the big d to the q dimensional vector with some hash function capital H, which is the sum of all the little hash functions for each of the sketches, mod k, and then with a sign function, which is the product of the sign functions. So my point here is that you don't have to explicitly expand this out, which is huge, and then apply a count sketch to it. Instead, you can take count sketches on each mode, that's each of these individual vectors, and you can multiply them together in a certain way, described in this bullet, to get a k-dimensional vector, and that would have been equivalent to expanding everything out and applying a count sketch with this hash function and this sign function. Okay, so I'm not going to show why that's true, but what this gives you is an example of how you can sketch a tensor product without explicitly forming the tensor product. And that's useful. So in kernel regression, you can replace A with S times A, because you're sketching each of the columns of A. And so that speeds things up. There is some issue with this original construction, which is that the sketching dimension K for this to work needs to be at least 3 to the Q, where Q is the number of modes in the tensor. Without getting into too many details, you can improve that to polynomial in Q. The rough idea is to take tensor sketch of 2 of the modes at a time, and that will square the dimension, but then you can sketch it back down and then take 2 modes at a time again. You can build a binary tree, and if you do it, you can get a polynomial in Q dependence. So I'm going to skip the details, but like you would think, oh, just make a binary tree. This will square the dimension. This will square the dimension. This will now make the 4th power of the dimension. But the point is, once you square it, then you sketch it back down to the original dimension, and you square it, you sketch it back down. And so when you do it again, you just get the square, and so on. Okay, so I don't have much time for low-rank approximation, but let me just say what the goal is and what the results are. So if you have a big data set, a big matrix, you might want to approximate it by a low-rank matrix because it reduces parameters and so on. And so we already solved the SVD. If A equals U sigma V transpose is the SVD, you can get an optimal rank K approximation from many different notions of optimal by just taking this sigma, this diagonal in the SVD, and zeroing out all but the top K entries. That's perfect optimal, but it's slow. Okay, so by optimal I mean it's the minimizer, for example, to the sum of squares, which is the Frobenius norm. But it's expensive. And instead what you can do is use sketching to instead find a rank K matrix A prime, so that instead of being the optimal, its Frobenius norm or Euclidean norm cost to A is at most 1 plus epsilon times the optimal cost. And if you allow for this relaxation, you can do it in number of non-zero entries of A plus n plus the poly K over epsilon. Okay, so you should compare this to SVD, which is nd squared time. Even if A is a dense matrix, this is at most nd. And so the whole thing would be at most nd. So it's much faster than the SVD. Yeah, I guess I'm running out of time, but yeah, let me just skip why that works. And let me just wrap up. So sketching is used for lots of other things. I just wanted to give you a glimpse. This is a tutorial. It's useful for so-called CUR decompositions, where you have a low-rank matrix and you want your low-rank factors to be actual subsets of columns and rows of your input. It's useful for dimensionality reduction, for clustering problems, for different big data models. It naturally makes your data smaller, easier to communicate, easier to stream, and so on. We saw it useful for speeding up first-order optimization, gradient descent. It can also be used to speed up second-order optimization. It's used in state-of-the-art linear programming and many other things like trace estimation and so on. And if you're interested, I have a monograph on this. And so that's all. Thanks. I will admit that I wasn't entirely sure what the audience will be, and I still don't know, but I do know that this is part of a machine learning workshop. I confess that my talk has very little to do with machine learning, but if you take a broad view of things, maybe you will find connections. What I was asked to do was to arrange for something that's a kind of tutorial / intro style, and I don't know if I'll quite meet the requirement of being a true tutorial. The talk is going to be somewhere between a tutorial and a survey. Okay, so I'm going to talk about streaming algorithms for graph problems. David has, of course, set the stage already by talking about, well, maybe not streaming per se, but something that's very adjacent to streaming. Our central concern is that we have a lot of data and we want to process it using memory that's much less sublinear in the amount of data. If you want to put slightly more precise notation on things, think of it as the input is a huge set of data items, m of them, from a huge universe of size n, and you want to compute some function of this data using space that is sublinear in both m and n. So there's two flavors of streaming algorithms that are common. Actually, those who came to David's talk in the morning, you've seen more of this. So there's the vanilla stream, which has items arriving one by one, i.e. items are inserted into a data set, and there's no notion of deletion. And in a turnstile stream, items could be added or deleted. So items either arrive or depart. And I'll say something about each kind of streaming as we go through this talk. There's a whole bunch of well-studied problems in the literature on data stream algorithms, which is now, I think, at least 30 years long. That is even counting the modern history, not counting some old works from the 70s. And so these are I just put down a bunch of problems that are things that people think about and would be considered very elementary in this field. Okay, so I'm not going to talk about any of this. This talk is about graph streaming algorithms, right? So there's lots and lots of things in streaming per se. Now for graph problems, so once you have the streaming model set up and you're starting to design algorithms with space in mind, then the next thing to think about is, okay, what about this, our favorite list of graph problems which theoretical computer science loves, right? Since the inception of computer science. Okay, so, right, if your input is a graph G, which you should now think of a very large graph that is too large to maybe store and process in random access memory, then as a stream it can be thought of as the edges of this graph arrive one by one. So you get to see each edge and then you do something with this edge and then it goes away. What you don't want to do, of course, is to store everything and then you have, that's more than you can afford to store. However, what I will say is that the edges are of an n vertex graph, and I will think of this n as being tolerable in terms of storage. Okay, so it is okay to store something that is about n bits long, but it is not okay to store the whole graph, which would be about n squared bits long in the worst case, right? Okay, now in a moment I'll give you a precise reason why this is the right space in which to be thinking about problems. So there's a number of well-studied problems in graph streaming. In fact, already even graph streaming is, I was looking through one of the earliest references that really got this field going, and that is now 19 years old. So there's close to 20 years of work in graph streaming. There is no way that I will summarize any meaningful subset of it in a short talk. So I will have to pick and choose. Okay, so I'm going to say a little about these problems that are highlighted over there and let the others slide, not because they're unimportant, but because I have to choose something. And even among the highlighted problems, I'm only really going to be talking about basic stuff. Okay, let's dive into it. Let's look at our first graph streaming algorithm. Very simple problem. Is your input graph G connected? Yes or no, right? Remember, you get to see the edges one at a time, not the whole graph. But then you can do something very simple. You just start by having an empty forest on your n vertices. Remember that n amount of storage is considered okay, and so that's kind of what we're aiming for. Each time we see an edge in the stream, we just check, does this edge complete a cycle with what's been stored? If it does not complete a cycle, then we take in this edge, we retain it. Otherwise, we discard it, okay? Hopefully the colors are coming through here. So if the blue thing is what you've stored so far, the forest F is that you've stored so far. If you next saw this red edge, you would discard it because it completes a cycle, whereas if you saw any of these brown edges, you would retain. That is the entirety of the algorithm. In the end, if you found a forest that connects all the vertices, then the graph is connected. If you didn't find it, it's not connected. It's quite trivial to see that this algorithm is correct. There's really nothing more to say. It's deterministic. It runs in one pass. It costs n log n space, right? And if you count in terms of bits. Now, you can ask, is this good? Okay, so I've been telling you that, yeah, space proportional to n should be considered good. Okay, why is this good? Okay. So let's talk a little about that. And I'll introduce a term here that we'll be using throughout the talk, the term semi-streaming. Okay. So m, which is the stream length for a graph, could be as big as n squared. Right? So in terms of m, this space is sublinear. It's not super sublinear, it's only square root of n squared, but it is sublinear. And the term semi-streaming, I have a feeling the semi here refers to the fact that it's square root of n squared. So the exponent half in the square root is what I think the semi is capturing. Anyway, the term was introduced by people who wrote kind of the first paper on graph streaming algorithms, and it stuck. So whenever you see semi-streaming throughout this talk, what it means is an algorithm that runs in n times polylog n space. Okay. Now, before I say anything further technical, I just want to caution people here that this talk is definitely not for data streaming experts. So if David is still in the room, then yeah, if he's not in the room, then he's made the right decision. I will spend most of my time discussing old results. So in a sense, I'm hoping that several of you are not familiar with graph streaming algorithms, in which case this is good because it gives you a bit of the lay of the land. Okay? You get a sense of what are the different kinds of problems people consider, what kinds of algorithms are out there, but it's still going to be only the elementary ones, right? So not the most up-to-date and kind of sophisticated algorithms with bells and whistles. Okay. Right, let's go back to this connectedness algorithm and ask ourselves, why is it okay to settle for about order n space? Why couldn't we ask for more? So here I can give you an actual proof that better than n space is actually not possible. The reason it's not possible is because I can solve this communication complexity, this communication problem called set disjointness, which consists of the following things. So if you've not encountered communication complexity before, don't worry, you've probably heard of set disjointness. Here's what's going on. You have two players, Alice and Bob, each of them has a set. Now these are small, it's shown here, but think of these as huge sets from some huge universe. Now they want to talk to each other and answer the question, are these sets disjoint? Yes or no? Okay. So this problem can be reduced to this graph connectedness problem as follows. So Alice takes her set X and converts that into a set of edges. So she puts in edges from S to, these vertices correspond to elements of the universe. She puts in edges from S to those vertices which do not belong to her set. And Bob does the same at his end. So now, if there's an element that belongs to both sets, then you will see that because of this construction, that vertex will end up being connected neither to S nor to T, and it will be isolated. So that makes the graph disconnected. In all other cases, the graph will be connected. So this particular graph, being connected or not, reveals the answer to the set disjointness question, which means any algorithm for connectedness has to be solving set disjointness. Now it is true that set disjointness is a communication problem, this is a streaming algorithm, but there is a kind of easy connection between the two, which, following David's lead, I will at least write something on the board. So, if you were to take Alice's input, convert that into the edges of that graph, and then describe those edges as a stream, right? And then Bob does the same with his edges. Alice and Bob can now implement a communication protocol for disjointness by running some purported streaming algorithm for connectivity on this set of edges, followed by that set of edges. So the communication that needs to go from Alice to Bob is exactly the memory contents of the streaming algorithm.
So if the algorithm is too good, then the communication will be too short, and a short message cannot solve such disjointness. That is sort of the fundamental theorem from communication complexity that we use. So using that, it follows that deciding whether a graph is connected or not is going to require omega n space. And this is going to be true even with multiple passes. The algorithm that I showed you was only one pass, but even if the algorithm made multiple passes, what that amounts to is saying that Alice and Bob can just go back and forth, but disjointness is still hard in that setting. Okay. Right. This is the only lower bound that I will talk about in the whole talk. The rest is entirely about upper bounds. There's a lot of interesting work about lower bounds in graph streaming, but anyway, that's not in this talk. Okay, so this is why semi-streaming is a good thing to aim for and often the best you can hope for. Yeah. Yeah.
So for different graph classes, do you expect better lower bound, better algorithms and
That's certainly possible. That's certainly possible. You could ask for an upper bound that's only true for certain types of graphs. Although if the graph itself is going to be sparse, then maybe you have to you'll have to question the model itself. Yeah. Okay. Fine. Let's see another algorithm that's kind of in the same spirit as what we just saw. Actually, we will see two more algorithms that can be thought of as variants of what we just saw. That extremely simple algorithm that we just saw. But the sophistication will start increasing in their analysis. So this is distance estimation, right? So you're given a streamed graph G, and you must process it using low memory so that in the end you can answer questions about what is the approximate distance between U and V. So after you process the stream, you will be given two vertices U and V, and you have to report the approximate distance between them. Okay, so here's an algorithm for this problem. It's kind of a variant of what we just saw. Retain edges according to the following rule. So here we have a current set of edges, which I'm calling H. When a new edge comes in, you see if it forms a short cycle. If it does, then you throw it away. If it forms a big cycle or possibly no cycle at all, then you retain the edge. Alternative way of saying this is if the distance between U and V in the current graph is more than t, then you retain the edge, otherwise you don't retain the edge. Okay, so this is it. So the set of edges that is stored by such an algorithm form something called a spanner. It will have the following property. This is a fairly easy thing to prove. So any edge that was discarded because there was already a short path between its endpoints, which means that the loss incurred from discarding this edge is to blow up the distance by a factor of at most t. Right? Makes sense? So any edge that I threw away is paid for by some alternate path which is at most t longer than the original edge. Okay. So here, of course, my graph is unweighted. There is a weighted version of this algorithm as well with basically the same idea. But anyway, this is unweighted. So what this short argument shows is that this subgraph H that I construct in this manner has the following property. Of course, it's a subgraph, so all distances can only go up, but they only go up by a factor of at most t. So this is called a t spanner. Okay. So we have an algorithm that gives us a t approximation to all distances, but how much space does it use? So the previous connectedness thing, I was storing only a forest, so I knew that the size of what I store is linear. Here I'm storing a subgraph which is not quite a forest but has this property that the girth is high. So the girth is defined as the length of the shortest cycle in the graph. Right? So the girth is at least t plus 2 by construction. And this, by a result in extremal graph theory, it's not a very hard result, but it takes a little work to prove. I won't do it. But using a known result, the size of such a graph is at most n to the power something less than 2. So n to the power 1 plus 2 over t. And therefore, we have an algorithm that runs in space. This is not semi-streaming anymore. It's not n polylog n, but it's bigger than n, but less than n squared. Right? So it's still sublinear. Okay, so this remains the best we know for this problem in the general case. Right? To this day, this algorithm is about 20 years old, 19 years old, and we don't know any better. So that's kind of interesting. Okay. Before I move on to something else, any questions so far? Yes, please.
Are there lower bounds for this?
Yeah, so there are no lower bounds known for the problem. Yes, so there are some lower bounds known for distance estimation, yes, but nothing that would be comparable to this. Now, what is known is that if you want the construction to be a spanner in this sense, if you want a subgraph of G with this property, such a subgraph must have size basically this, assuming some conjecture in graph theory, well-known conjecture called Erdős-Gerth conjecture. So I guess the answer is there aren't really any lower bounds, but if you believe in a certain long-standing conjecture, then yes, there's some kind of conditional lower bound. Yeah.
What if we have multiple passes?
Yeah. If you have multiple passes, it gets interesting, and there are certain things you can do. Yes, I won't go into that for this particular problem, but yes, so there is a saving possible. Yeah.
Why is the space required for connectedness n log n?
Why is it n log n and not n?
Not n.
It is actually okay. So the lower bound that I showed you only shows you, and you can go higher. Yes, you have to. It requires a more sophisticated argument. Yeah. Okay. So, you're saying why was the upper bound n log n in what I said?
Yeah, not
Oh. Okay, good. The number of edges you store is n. However, the name of an edge requires log n bits, right? So you have to write down the two endpoints. Yeah. Good. Sorry, I didn't understand your question the first time, but yeah. Okay, so let's switch gears and look at a different problem, maximum matching. There will be two more gear switches as in changing to a different problem. But the nature of the algorithm will be similar to what we saw before, so it will hopefully not be a jarring switch. So of course, I hope we all know what a matching is, a set of edges that are independent. You want to find an approximately maximum weight matching in the graph. There need not be weights. The question makes sense and is interesting even when all weights are 1. So then that's called a maximum cardinality matching, or MCM. So first let's think about just cardinality. Here is an algorithm for maximum cardinality matching. As the edges come in, simply pick a maximal matching, i.e. pick an edge if it doesn't intersect anything previously picked. That gives you a maximal matching. It's a greedy maximal matching. As is well known, or you can prove it easily too, that would be a 2 approximation. A maximal matching is at least half the size of the best matching. Okay? Now some people would call that a half approximation. I just like to call it a 2 approximation. Some people like to call it a 2 approximation. I'm in that camp. All right. This would be a semi-streaming algorithm. It gives us a 2 approximation, and this trivial thing is the state of the art. No one knows how to do better. At least not if you, not unless you lose on something. So if you want a one-pass semi-streaming algorithm that approximates MCM, the best thing you know is to do this completely trivial thing with absolutely nothing to it. There's nothing to the analysis. Yeah, right. This to me is the most embarrassing open problem in graph streaming. Okay, now for maximum weight matching, okay, here you could use some cleverness. So let's see an algorithm in the same vein as what we saw before. So we'll have some simple rule for either retaining or discarding each edge as it comes in. Okay, so each edge has a weight now, right? So when an edge comes in, it's got a certain weight. And we will do something that seems pretty natural. So the blue edges show what we have retained so far. There's a current matching. When a new edge comes in, if this new edge, okay, so let's look at this edge over here. So I want to take this edge because I see its weight is 9, which is kind of high. It's a nice edge. I like it. But of course, if I take this edge, then I can no longer take this edge or that edge because that would not be a matching anymore, right? So they conflict. So I will discard these two edges and take this edge instead. So I replace a weight of 6 with a weight of 9 because 9 is significantly better than 6. Okay, that's my logic. Whereas over here, this edge has weight 9, but if I were to take this edge, then I would be throwing away 8 units of weight. And I'll say 9 is not significantly more than 8. It is more than 8, but it's not significantly more. So I will discard this one. So that's the rule. So in general, there's some parameter alpha that controls how much more is significantly more. Right? So if the newly seen edge has weight that's at least 1 plus alpha times what it would be evicting, then I will in fact take the new edge and evict what it conflicts with. That's the overall logic. So why is this a good matching? Okay, so this is one where it actually takes some proof, and while I could do it, I want to talk about a few other algorithms, so I'd rather not do every last detail of the proof, but I'll give you a flavor of the proof. So general style of these proofs, and by the way, this goes for not just this algorithm which I'm showing you, but for a whole bunch of maximum matching algorithms in streaming. Right, so they all operate in this way. So consider some optimal matching M star, which we are of course not computing. It's got a set of edges, but each edge in this optimal matching is going to generate, this should be E star, sorry, that's a typo. It generates W E star amount of charge, right? So this is W E star is its contribution to the optimum solution. And so let's say that's an amount of charge that this edge generates. Now our actual output may or may not have this edge in it, in which case we will take the charge of this edge and spread it in such a way that it's accounted for by the edges in our actual solution. Okay, so the algorithm's decision will be used to transfer all these generated charges to the edges that are actually in the final output matching. Okay? And this will be done in a way so that we can argue that this charging scheme will tell you that the amount of charge that's generated is the amount of charge that ultimately remains in the graph, and there'll be a way to account for these charges based on the vertices of the graph that gives you an inequality of this form. So so once you do this per vertex accounting of the charge, you'll be able to prove a bound that looks something like this. So where this particular function came from, you can't really see unless I go through the whole proof. But trust me on this, you get a function like this. So once you have this kind of inequality, you just optimize for the best parameter alpha. That's an easy thing. Once you do it, you get this particular approximation for the algorithm that I just presented. Now there's nothing to say that that algorithm was the right way of deciding when to retain or discard edges. So you could use other strategies, and if you do them, then you get various other algorithms in this general family. So there's something that I did with a former student which generalizes matching to maximizing a submodular function rather than maximizing just weight, and you can use similar ideas to get an approximation algorithm there. And then for the matching problem itself, there's this really landmark paper of Paz and Schwartzman, I believe a best paper award winner at SOTA, and then a follow-up which kind of simplifies the presentation and analysis that gets us a 2 plus epsilon approximation to maximum weight matching. This remains the state of the art in a single pass. Yeah. So they too are basically, it uses a somewhat more complicated rule for what to keep and what to discard. But ultimately the analysis comes down to this same kind of charging and charge transfer scheme and a per vertex accounting of charges. Okay. So any questions on? Yeah, sure.
So what factor do you get for submodular maximization?
In our algorithm, it's like 7.7 or something like that. That's not the best. It's been improved since, but the improvements are not quite following this scheme. Yeah. And there was something at the back. Yes.
Can you do better for bipartite graphs?
Can you do better for bipartite graphs? Yes, sure, you can. Yeah. That's right. But again, not. Yeah, you have to do something a bit more ad hoc for bipartite graphs. Yeah. But by better you mean better factors, right? Yeah, sure, you can. Okay, so let me just mention, so there are all sorts of questions you can ask about, what about bipartite graphs, what about triangle-free graphs, things like that. All of this has been studied. In fact, there are so many papers on matching in a streaming model that I think merely listing all the papers would fill 2 columns of a slide like this, right? In small font. Okay, but let me just mention a few things that I'm not going to talk about more, but just to tell you that it's out there. So that was a 1-pass algorithm that we just saw. If you allow yourself more passes, then you can do better. That should not be surprising. And at a high level, for maximum cardinality matching, what happens is you use your additional passes to find augmenting paths to improve your current matching. So you use your first pass to do something very simple, very greedy. But subsequently, you use the current matching that you have to guide which edges are interesting and which edges might make good improvements to your current matching. So using this idea, McGregor gave a 1 plus epsilon approximation in some constant number of passes. You think of epsilon as a constant, but pretty horrible function of epsilon. So that was randomized. It was then made deterministic by Tirodkar some time back. So I guess you can see there's a big gap between this paper and this paper. So somehow interest in the matching problem has increased lately. Okay, so as recently as a couple of years back, Fisher et al. Gave an algorithm in polynomial 1 over epsilon passes, okay, which is I think that's the current state of the art in terms of passes and 1 plus epsilon approximation. For the weighted case, again, there's a long line of work. But here, the additional passes are typically used to do some kind of multiplicative weight update. And this may be my closest connection to something that's actually machine learning. So machine learning people will know what this is. Just to be clear, the weight in this case does not refer to the weights of the edges in the graphs. There's maximum weight matching, the edges have weights. These weights refer to importance in the sense of multiplicative weight update. If you don't know what that is, never mind. So there is a way to use LP duality and this MWU framework to do some kind of gradual improvement with additional passes. So An and Guo pioneered this technique, and they got a 1 plus epsilon approximation with a number of passes that's not quite constant. There's a log n in here, and I think as of today, there's two this is one kind of state of the art result, and then there's another state of the art result which removes the log n dependence. So it's entirely a function of epsilon, but again, it's a pretty high exponent. Okay, so I didn't mention the exponent here. This is, I think Safer Asadi calculated this to be 19 at least. And this is guaranteed higher than that, because this kind of uses that idea as a subroutine. Alright, I'll have to say that these algorithms are super complicated, perhaps among the most complicated algorithms out there in graph streaming. And so, there's a new paper by Asadi this year which does a nice job of simplifying some of what's going on here. And if you're going to study any of these algorithms, I'd suggest studying this one. It's a beautifully written paper. So he gives a simple, easy to understand, and easy to analyze 1 plus epsilon algorithm, 1 plus epsilon approximation in 1 over epsilon times log n passes. Okay, all of this is in the semi-streaming space. There is work on what can you do if you allow yourself more than semi-streaming space as well. But anyway, there's just too much to mention, so I shall move on. Okay. Now I'll actually switch gears to a different problem. And the timekeeping note, what time is this supposed to end? 3:35? Okay, yeah, no, we're good. Yeah, so you're going to ask something?
Yeah, so with recent progress in dynamic matching, like, do you see any connection with this? Because there was a 2 hours long standing.
Yeah, there seems to be parallel improvements on both ends. So yeah, that's the best that I can say, because I don't think I am expert enough to understand how to translate the dynamic algorithm progress to this world. Yeah. So in fact, do you know something about the technique underlying this dynamic? Do they use MWU?
Yeah,
So if they're using MWU, there's a chance that there is some similarity in ideas.
also expanders they use a lot. So spanner, whatever.
Yeah. But just in case somebody else is wondering about what Arindam was asking about, so there's this line of work on dynamic algorithms where the issue is how much time you spend processing each update. It's not really, space is not their primary concern, but they think of it as an evolving data structure which, with each edge addition or deletion, you want to make minimal changes in your data structure to continue answering these questions. So there are some parallels between improvements in that world and improvements in the streaming world. But more precisely, I don't know. Okay. All right. So talking of dynamic, let's talk about dynamic algorithms. Now, for us in streaming, the word dynamic is going to mean simply that edges can either arrive or depart. So what is called turnstile streams. So let's go back and look at our first problem of connectedness. All right. So that simple algorithm we had of
Sorry, before you
Yes.
move on, so for this kind of graph algorithms, if your edges follow a certain order,
Yeah.
just a random, like say I start from my nodes and then do some BFS and then edges come in that order.
Yeah.
Does that make the problem easier?
It could very much make the problem easier. I think, in fact, a number of lower bounds will not work anymore, and I suspect certain problems would be decidedly easier. Yeah. In fact, multipass, somebody asked about multipass algorithms for connectedness, and the best multipass things we know today involve basically simulating BFS in some way. So if you're going to get your edges in a favorable order for doing that, that's bound to help. Yeah.
Random order, does it help?
Random order is also it. Yeah, yes, with regard to matching, it's been studied. With regard to a few other problems as well, and it helps. There are many problems where we know it helps. For matching, it helps. Also for triangle counting, which I'm not going to talk about, but yes, there are many graph problems where that helps. Yeah. Okay. So now here, your edges may be inserted or deleted, and at any time you have to answer whether the graph was connected or not. Obviously, it's no longer a viable strategy to maintain a spanning tree, because if you maintain a spanning tree and an edge goes away, then you have no idea what to replace it with. Right? You clearly need to do more. Okay, so this is going to take a whole new approach, and such a whole new approach was pioneered by An, Guha, and McGregor. This is a paper that's worthy of a test of time award. Hopefully, it will happen soon. Okay, so before I present their algorithm in the streaming setup, let me just reframe the problem like this. So think of each node of this graph as being a player in a communication game. And each player only knows their own neighborhood in this graph. So the players are all going to send messages to some central coordinator who's going to look at these messages and then decide whether the graph was connected or not. Okay? So these messages are simultaneous. Okay? So suppose I had a low communication protocol in this setting. I claim that that will give me a streaming algorithm as well, because what I would do in a streaming version is maintain each player's eventual message to the coordinator as the edges come in, right? Now, I guess it matters that the messages have to be formed in a certain manner so that you can compute everything in streaming fashion. But the streaming algorithm will basically say at each vertex, you maintain a sketch which will ultimately become the player's message to the coordinator. So when the stream ends, then the players virtually send messages to a coordinator, and we virtually run the coordinator's algorithm to determine the output. Right? Okay, so here's the main algorithm that we will run in that framework. Alright, so if you kind of stopped paying attention earlier, then this is a good slide to pay attention to, because like I said, this is an idea deserving of a test of time award. It's a beautiful, beautiful idea. So the authors did not give the algorithm a name, so I'm going to give it a name. Merge clusters using boundary edges. Okay, M cube, if you read it, right? I'm going to call that M cube. Right, so here's what it does. So given a subset of vertices, I'm going to have some oracle. I'm going to implement some oracle, which I'll call B, which returns a boundary edge from the set S. So what's a boundary edge? So this is a set S, then any edge that leaves that set is called a boundary edge. Okay? The boundary is denoted by this partial symbol del. Okay? So suppose I had such an oracle. Okay? So forget about how I get such an oracle, but suppose I had it. Then I would run the following algorithm to determine connectedness. In fact, it will return me a spanning forest of the graph. Okay? So if it is, not only will it tell me whether the graph is connected or not, it will actually give me a spanning forest. Okay? So I can count how many components it has and everything. Start with an empty forest and run the following loop. So at all times, we'll have some forest f. So here the algorithm is run for a certain amount of time, and we have these blue edges, which are our current forest. Our current forest gives us a bunch of connected components, right? So in this case, there's that one, that one, that one, that one. There's 4 components in this graph. So each component has a boundary. So I'm going to query the boundary sampler, which will give me an edge from each boundary. So let's say it gives me that edge from that component, and then that edge from the singleton component, and then maybe that edge from that component, that edge from that component. Okay, so I sample 4 times for the 4 components, and now I have 4 sampled edges shown in pink. Okay. So the next thing I'll do is I'll merge the components along these pink edges, because that's what's going on down here. Right? So this last line is saying, take a new spanning forest of the graph by adding in these pink edges and sort of recomputing connected components. So what this has done is it has merged the original 4 components into only 2 components. Okay, so this operation should reduce the number of components, and it's not hard to show that each iteration is going to at least halve the number of clusters, number of components. Okay, so each component finds a new one to connect to, unless of course we have reached the. So where does this converge? So if the original graph was connected, eventually this is going to all merge everything into one component. If it wasn't connected, at some point we are not going to be able to grow the components anymore, and we stop and we have our spanning forest. Yeah. Okay, so it remains to show how to implement this M cube algorithm, i.e. how do you actually get this boundary sampler, this magic device that gives us an edge out of each component. So for this, we will look at the signed incidence matrix of the graph. There was a talk this morning which brought up the signed incidence matrix. I forget now in what context it came up, but it definitely did. Karthik was talking about this. Yes, Karthik's not here now. You could see that. Anyway, good. So this, for those of you who were at Karthik's talk, this is the same thing. If you weren't there, it's a simple idea. We just take the vertex edge incidence matrix. So this is a matrix with one row per vertex, one column per potential edge. And instead of writing only a 0, 1, we write a 0 or plus minus 1. We write a 1 if the edge leaves from you to go to a higher numbered vertex. And we write minus 1 if it leaves from you to go to a lower numbered vertex. Okay, that's it. Now, if we have this, I claim we get a boundary sampler because, okay, let me show you something here. I will come back to that slide in a moment, but I want to show you something here. Okay, there's one claim being made here which is important to prove. Okay, so you see this little claim here. So the row corresponding to a vertex is, let's say, B sub u. Then I claim that if I add up the rows corresponding to vertices in a set S, then the support of this vector is exactly the boundary of S. Okay? So let's see that. It's best to see this with a little example. So here's a simple graph, only 4 vertices. So if there's 4 vertices, there's 4 choose 2 potential edges over there. So then just write down the matrix following the rules that I was explaining. Now if you were to take S equals 1, 2, so this set S 1, 2, just add up the corresponding rows. So you add row 1 and row 2 and you get this. Notice where the non-zero entries are. The non-zero entries are here and here. So the edges 1, 3 and 2, 3. Those are exactly the edges that cross this cut. They are the boundary edges. Now similarly, if I take S equals 1, 2, 3, so now imagine the vertex 3 is also pulled into this cluster. If I add rows 1, 2 and 3, I get a vector with only a single non-zero entry. And that corresponds to the pair 3, 4. And yeah, remember if this were the cluster, then 3, 4 is the only boundary edge. Okay, so the reason it works, of course, is that anything that's internal to the cluster will cancel out because it'll appear as a 1 and a minus 1 in 2 different rows. Okay, now with that observation, let's go back to the algorithm itself. So suppose we have an L0 sampling sketch matrix. Okay, I realized that David didn't talk about L0 sampling. I saw that he was giving a talk about sketching and I was hoping this would come up, but that's not what he was talking about. Do folks know what L0 sampling is? A show of hands, maybe how about a show of hands if you don't know what L0 sampling is? Okay. Okay, I'm glad that there's a number of people who are willing to admit that they don't know this. That's okay. It is bread and butter in streaming, so you may as well know it then. So what L0 sampling does is you have some high dimensional vector x. You're going to sketch it using some matrix L. And we now have a much lower dimensional vector Lx. L, of course, is random. Now, what we want is that by looking at Lx, I should be able to run an algorithm, some algorithm called extract, which will return to me a coordinate I, such that xi is non-zero. Okay, so this is what it does. Oh, so in other words, I is in the support of this vector x. Right? And it returns all such I with equal probability. Or approximately equal probability, say. So, in other words, it gives me a way to uniformly sample a coordinate from the support. So such a sketch exists, so it is possible to get a good linear sketch which supports that operation. So that's called L0 sampling. So suppose we have that, right? We do have that. There are known constructions that do this. Then what I will have to do is maintain a sketch for each vertex using this sketch matrix L. Right? Now if I wanted to sample for the boundary of a particular set S, I simply add up the corresponding row vectors and take the sketch of the sum of those vectors. But since this is a linear sketch, the sketch of the sum is equal to the sum of the sketches. So if I maintain the sketches, then I can add the sketches. And that's it. And then I have a way to sample from the boundary. So this is how I can implement the n-cube algorithm. All that remains is to account for the space, So we need log n iterations of m cubed to sort of merge the clusters together. Each single iteration of m cubed is going to need log squared n dimensions for the L0 sketch. Okay, that's what the result. I didn't tell you what S works there, but log squared n works. And then I have to implement such a sketch at each vertex. So if you multiply this all together, the space is n times log cube n. Okay, so that is semi-streaming space. Okay, yes. So I think this is one of the most beautiful graph streaming algorithms out there. Okay, I'll switch gears one last time to talk about one other problem, and then we'll wrap up. Yeah, so I don't have a whole lot of time. I might skip some things in this, but still I'll give you a flavor of how to color a graph well. Okay, so you have a graph. You want to color its vertices with a small number of colors so that non-adjacent vertices get distinct colors. That's called a proper coloring. Chromatic number is very hard to approximate. We know this in the traditional computing world, but we are not going for anything like the chromatic number. So here we'll say that the graph has some bounded degree, delta, and we only want to color the graph with, say, about delta colors or some function of delta colors. Now I know for a fact that I can always color with delta plus 1 colors, right? I'm sure you've seen this in some undergraduate graph theory course. And the method is simply to color greedily. Just take any vertex, color it whatever you want, so long as it doesn't conflict with what you already have, and this will just work. You'll never get stuck. Okay. All right, so you do that, and if you color like this, you end up with, in this particular example, we ended up with a 6 coloring, 1 green, 5. Okay, 5 coloring. All right. If you are going to be greedy, there's a slightly smarter thing that you can do. Let's introduce this parameter kappa called the degeneracy of the graph. It's defined as the minimum number k, so that every subgraph has a vertex of degree at most k. So if you remember your graph theory, then in a planar graph, this number is guaranteed to be 5. Okay? And I mean, in general, so a planar graph does not necessarily have bounded degree, right? So the max degree could be very high, but this number is at most 5. So in general, the degeneracy could be a lot smaller than maximum degree. And you can change delta plus 1 to kappa plus 1 by running the greedy algorithm in a suitable order, right? I won't say more about this, mainly because these are not streaming algorithms anyway. They are greedy, which means they need the whole graph to be there so that they can make their decisions. But you can use these to do something in the streaming model. So sometime back with former students, Bera and Ghosh, we showed how to color a graph in a streaming fashion with something like the degeneracy number of colors. The idea is to partition the vertex set into clusters at random and choose the number of clusters carefully so that each cluster ends up having low degeneracy. Because again, a picture is worth 1,000 words here. So let's say here I have partitioned it into 3 clusters. The clusters certainly need not be anything respecting the topology of the graph. It's just a random partitioning. Okay, so there's green, blue, and this whatever gold. We only retain the intra-cluster edges, and we throw everything else away. So what we're doing here is we are committing to using disjoint palettes for the distinct clusters, okay? Which is why we don't have to bother about any inter-cluster edges. They will not be conflicting because we'll use disjoint palettes for them. Okay, so you'll see that at a very high level, what we're doing is saying the graph coloring problem as such is not constrained enough, and this is why it's hard to find algorithms. But if we over-constrain the problem, we add an artificial new constraint, now it's possible to do something in streaming. Okay, so what the over-constraining does for us is it makes sure that we don't have to store too much. And yeah, so in the interest of time, I will not try to say more about this, but with this idea, we can get a semi-streaming algorithm which uses a number of colors that's just a little more than kappa. So remember, the combinatorial optimum would be kappa plus 1. And then again at a high level, Asadi, Chen, and Khanna gave a completely different algorithm, but you could say that at a high level it over-constrains the problem just like we over-constrain the problem, but it's a different kind of over-constraint. So what they say is choose at each vertex a random subpalette of size order log n, right? And now we commit to coloring each vertex only from its subpalette. Okay, once again, let's see it by picture, it's much easier. So they choose a random list at each vertex, right? And then they say, since I'm committing to coloring this vertex only from this list and this vertex only from that list, and these lists are disjoint, I don't care whether this edge is there or not. So I will only retain edges between vertices whose lists intersect. So if I do this, then again it cuts down the amount of storage. I need to store only a small size graph, gives me semi-streaming space. But they are left with a somewhat difficult task after this, which is that they have to color whatever was retained using colors from the lists that they have committed to. And this could be a hard problem, and it actually is. So they have to run something somewhat sophisticated offline to solve that problem. But they can do it, and net result is that they get an algorithm to produce at most delta plus 1 colors. Okay. So I think I'm done with all the algorithms that I was going to say. In the interest of time, I shall not talk about further work on coloring. This is just a summary slide. Let me conclude with a couple of very, very sparse slides. One, to say that I've left out a whole bunch of things, because I told you that I would. Some of the most important topics that I've left out, I think, are the triangle counting problem, and more generally subgraph counting, pattern counting, motif counting, what have you. This is, after matching, this may be the thing that has the most extensive literature in graph streaming. And then I left out stuff about cut spacifiers, spectral spacifiers, max independent set, digraph problems. And then finally, I know Yusu was asking about alternate models of how the stream is presented. Another thing that is well studied and I haven't talked about at all is what's called vertex arrival streaming, where the edges of the graph arrive all the edges attached to a vertex arrive together. And in many problems that helps, and that calls for new thinking behind the algorithms. But I put this out there in the hope that if somebody came to this talk hoping to get a sense of what graph streaming is all about, this will help. Okay, I will just mention a couple of open problems that I think I've already said during the talk. The first one I haven't said. So for connectedness, the AGM sketchup, that M-cube algorithm, ultimately has to use randomness in order to do this L0 sampling. If I didn't allow you randomness, and you must be deterministic, is it even possible to get anything interesting? We don't know. So there's absolutely no lower bound known, and there's no upper bound known. So it's wide open what's going on here. And then for matching, I already said what is possible in one pass. Can you beat a factor of 2 for maximum cardinality? It's so embarrassing that we don't know anything about that. But yeah. So as open problems goes, I think these are the big ones out there. Solving either of these should put you in the territory of maybe you can get a best paper award out of that. Yeah. Okay, very good. Thank you for listening, and happy to take questions.
Welcome back, everyone. For our next speaker, we have Professor Chris Schriegel-Schon. Chris is an associate professor in the Department of Computer Science at Aarhus University. Specializing in algorithm design, Chris focuses on areas such as online, streaming, approximation, and learning algorithms. Previously, he was a faculty member at Sapienza University. Before that, he received his PhD from Technical University of Dortmund. Chris has an extensive body of work, including publications presented at top conferences like SODA, Fox, NeurIPS, and ICML. His research spans clustering, Corsets, dimensionality reduction, and fairness in algorithms. He's also a recipient of a Best Paper Award at IISa. Let's welcome Chris, and over to you.
Okay, so thank you so much, and thanks for everyone who managed to stick around. So today I'll give you the talk that I probably should have given in the morning, and should have swapped sessions maybe, because maybe you would have gotten more out of the morning talk if I had given this one first. But regardless, so it's going to be about Corsets in general, I suppose, but with a very strong focus on clustering. Let's dive right in to the motivation behind this. So here you see a picture of someone that isn't really completely rendered, and if I pride myself on one thing, I can use LaTeX. So this is deliberate, right? So basically I rendered it in its original resolution, and slides do not manage to fit the data that I have. So if the data does not fit, you could either use better hardware, or you could use an algorithm to make the most out of your hardware. So you're going to sketch it down, compress it, to get like big data into tiny data, and still have something useful. So that's kind of the theme that goes into Corsets. And Corsets are always designed for some problem. So you need to know which problem you're looking at. There isn't really a one-size-fits-all solution for all problems simultaneously, even though some of the results that I'm going to talk about today have a fair bit of generality. And the problems that I'm looking at are center-based clustering problems. So this captures k-means, k-median, k-center. You're given a set of endpoints and some metric space. Z is going to be a positive integer. You may think of Z being 1 or 2. Those are the interesting cases. 1 being k-median, 2 being k-means. And you now want to find a set of k-centers such that the sum of square distances is minimized. So yeah, okay. In wise anticipation, I already would have said something about k-means and k-median, but yeah, let's just go over this again. So k-median, Z is equal to 1. That's a little bit more robust to outliers. K-center, which corresponds to the limiting choice of Z going to infinity, is really not that robust to outliers. And k-means somehow strikes the balance between the two. And there are reasons to choose any one of those, right? So it's a design choice. It's not really that one is more preferable or better than the other. Okay. So a Corset. So Corset, for the sake of this talk, is going to be a weighted subset of the input points. So you're going to look at, you're going to select some subsets. You're going to weigh them in a probably not too, in a reasonable way. And then you're going to compare the cost of the original point set and the weighted cost of the selected subset, and you want those to be very close to each other. And this has to hold for all points at the same time. And Corsets in general, so if you're not trying to design this for clustering, but for some other function, basically, for any query that you could make to that function, the valuation has to be the same up to some small error on the Corset and the original for you to get away with calling it a Corset. Otherwise, you might get called out. Okay, so here is kind of like an overview as to where do Corsets fit in the bigger scheme of things. And it's also somewhat of a historical slide as to how Corsets evolved over time. So they originated with computational geometry, and back then, so the way that we treat corsets now was very thought of as very different back in those days. So in those days, I would say it was more like a data structure-esque thing or a means to speed up an algorithm. It really wasn't that much yet about compression and similar topics as what corsets would then become. So this is kind of like the second stage of corset research, when we realized that compressing data helps with big data algorithms and big data settings. So streaming, which is something that David talked about previously, or also Amit, is very easy to do once you have a corset for your problem, as we will see. And related models such as the massive parallel computation framework, not going to explain what that is. It's just like some hybrid between streaming and distributed computing. They also really benefit from corset constructions. And I would say something like the third stage of corset research, who knows if it's the final stage, but it is the current stage, is the strong connection to ML, right? So at least the problems that I'm going to talk about today, they're basically learning theory in disguise. And this was not really how the people who proposed the corset notion initially thought of it, right? But the whole learning theory aspect, that is how you probably want to approach corset design and corset questions, at least for the time being, until we enter the fourth stage, whatever that might be. Okay, so I felt compelled to include like one practical application. So the practical application that we're going to see is image segmentation. So you could actually run a corset for, this is indeed for k-means actually, for image segmentation. And here I'm now just going to vary the corset size and we can see what will happen. So if I use not too much data, then the image is kind of blurry, and as my corset size increases, the image gets better and better, and this is still like, I think, 5% of the size of the original image, so already quite good. Okay, so now let me tell you a little bit more about why corsets happen to be so useful, right? Before we're going to design them, why people cared about them in the first place. And the key word here is composability or mergeability. So let's imagine that, or suppose that I have all of the data that we perhaps collectively want to analyze stored at my own computer, and my computer is just not up to the task, so I want to use everyone's computers here. So what would I like to do? Somehow distribute the computation. And there's now an issue with the distributed computation that is about synchronization, that is probably, I mean, it's a compelling problem to maybe look at, but it's also a challenging problem, so maybe I would like to avoid that challenge if I could. And the nice thing about corsets is that if I just partition it arbitrarily in a disjoint way, and every one of you computes a corset locally and sends that back to me, then the stuff that I have is a corset of the entire data set, right? So corsets in that sense, they're almost embarrassingly parallel. You don't really have to, do much work in order to speed up your corset computation. Right there, there's almost no limit to the speed up that you can get if you have additional computational resources. So any dependency on n, like the number of points, I can mitigate almost entirely if I just have enough computation power at hand. Okay, and like also as a nice part, the fact that a corset is small also limits communication bandwidth, like other things that are important in distributed computing.
So the property that you're stating, don't A1 and A2 need to be disjoint?
Yes, so it's a disjoint. Didn't I say disjoint? But I mean, shame on me if I didn't. Yes, they have to be disjoint.
Maybe I misheard it.
Yeah. No, if they're not disjoint, then weird things can happen. Yes. Okay.
And if they're disjoint, it doesn't depend on the task structure?
So, and what I'm kind of saying is, if you have this composability we will, like the corset definition I gave earlier that has this property, and I would say that if you want to come up with a new corset definition, what reviewer 2 will complain about if it does not satisfy this property is, why do you call it a corset? It's something else, right? So I don't know that I necessarily agree with. So if it extends to all possible queries at the same time, it's usually composable, but you can design functions where this doesn't hold if I merge. But people nowadays, I would say, they take it as granted if you give, or if you say what you're doing is a corset, that it is mergeable to some degree. Right. Maybe not losslessly mergeable, as is the case here, but in some way mergeable. Okay, good. And the other very nice application is the streaming model. So this is just now going to be insertion-only streams. Dynamic streams behave a little bit differently, but there exists a black box reduction from insertion-only streams, from corset computation to insertion-only streams. So even if you've never encountered streaming before and are not that familiar with some of the sketching techniques that are out there, if you get a corset, you also get a streaming algorithm. And it works as follows. I read the first batch, I compute a corset of that. I read the next batch, I compute a corset of that, and then I compute a corset of the two corsets, right? So I throw away the old two corsets and just maintain the, right? So at this stage, the memory that I had to keep, those were just two corsets, right? And now I recompress it again into a new corset, right? And I'm going to continue doing this. So compute a corset of the next batch, take another point, take a corset of a corset again, remove those. Now compute a corset of these two and remove those again, and so on. And this way I'm going to process the entire stream and have kind of like a tree of active corsets, right? And the key property is that at every level of the tree, simultaneously, I only have one active corset. So you can just maintain this tree structure in a nice online fashion. And if I reach the end of my stream, the one corset that I get by consolidating and having recompressed everything, that will be a corset of the entire data set. Now you might ask, does this incur a loss? Indeed, it did in the original stages of corset research, at least in theory. In practice, it would always work. But in fairly recent work, Vincent Cornadat, David Woodruff, and Samson Su show that you essentially have no overhead in terms of the space requirements, right? So it's not just that you kind of get like a lossy reduction. You get almost no loss whatsoever. So Corset is, I don't know if I could say that it characterized the space complexity of clustering in streams, but it at least gets very, very close. Okay. So here are, if you want to get into corsets, I think you should read the 3 papers given right here. So I'll be mainly talking about clustering, but I would feel a little bit remiss if I didn't mention some of the results, some of the other results that are here. So the foundational text, that's the one by Pankaj, Zahir Hapelet, and Kasturi Varadarajan. It's in terms of the techniques and the problems they were looking at, like most foundational texts, that but it aged well, right? So it's a little bit out of date, but it aged fairly well. And the other important paper that I would like to mention is one by Ken Clarkson. This uses a fairly different notion of corsets called weak corsets that I won't really discuss all that much or at all even. But it revealed a very nice relationship also with optimization tasks. So corsets also somehow managed to touch upon that. And in terms of, I would say, or what I would call modern corset constructions, the first real modern paper, and still, in my opinion, the most readable one is the paper by Kitchen. Okay, so what will you see today? Well, you will see how the algorithmic techniques evolved for corset construction from the earlier, more geometrically inclined stages to the later, more learning theory inclined stage. And you'll see also kind of how the bounds evolved along the way and how the insights developed
as time went on. Okay, I won't go that deep into proofs. There will be a little bit of proofs. It was supposed to be a tutorial, but I think for the most part I'll just touch upon the different algorithms. Okay. Good. So roughly you can classify Corset algorithms for clustering by two ways. First are what I call geometric decompositions. So the idea is basically carve up your space, and the decomposition itself is your Corsets with an appropriate choice of weights. And the other type of algorithm are sampling-based algorithms. Right? So the sampling-based algorithms came later, so you'll have to bear for a moment if that's all that you want to know. I'll first talk a little bit about the decompositions. In spite of them not giving that great of a bound by themselves, they're still important, as we will see. Okay, so let's ask, so this here is like a nice problem that I like to give to students, show that this algorithm here doesn't work. Right? It's I think the first algorithm that PhD students working in Corsets would consider. Let me just compute an optimal M clustering for a sufficiently large value of M, and let's show that that is a Corset. Surely that cannot be too bad, right? And in some cases it's even easy to convince yourself that should be optimal, right? So how large do we have to choose M such that this works? And the bad answer is, well, it doesn't work at all. And there's a simple counterexample, an n-dimensional simplex. So you have a fairly easy closed form solution as to what the optimal K clustering in an n-dimensional simplex is, right? For K-means, the clustering cost is n minus m, right? And and all of those centers are very close to the origin. So you're really not gaining anything by adding new centers. So this idea, at least in high dimensions, it kind of breaks, and if it breaks in high dimensional Euclidean spaces, it will break for most metrics, right? So you really have to severely constrain your metrics if you want an approach like this to succeed. And the constraint that we're going to look at, and this is indeed what computational geometry typically is kind of good at, is, well, what happens in low dimensional Euclidean spaces? So let's consider this. Okay, so this was, I believe, the first Corset construction for K-median and K-means, right? So not the first Corset paper overall, but the first one for clustering. They had this idea, and yeah, again, we just add additional centers, if you will, move points on top of those centers, and then just weigh those centers by the number of points that were moved on top of it. And the Corset condition that they imposed is, yeah, well, if this movement cost, right, or the clustering cost to the Corset is not too large, if that is at most epsilon opt, for K-median at least, then your K clustering or M clustering will be a Corset. Now the proof is fairly straightforward. It is basically an application of the triangle inequality, right? So move everything by a little bit, and then you query it. You will pay at most the difference, which is this little bit, right? For K-means, there's like a little bit more work that but essentially you still have a triangle inequality for K-means as well, so it's not fundamentally different. Okay, so first idea that you could have is that let's just throw a uniform grid over this entire thing, right, and limit the length of the grid as to show that, you know, the movement cost is going to be at most epsilon times opt. And this indeed works for K-center. So for K-center, this gives you a Corset of size K times epsilon to the minus D. And this is also, optimal. You can improve the exponent of the epsilon. So I think epsilon to the minus D minus 1 over 2 is optimal. But yeah, essentially you cannot do significantly better. For K-mean and K-means, this doesn't really work, right? So if you want to use just one grid that you throw over the entire thing and the movement cost is not too much, then it's kind of like that the cells, they have to kind of anticipate a worst case movement, and you'll end up having just way too many cells. Every point will be in its own cell. So what we do instead is we scale the cells depending on the contribution of the points to an optimal solution, and it looks then a little bit like this. So let's imagine Okay, my color scheme is a bit off. That shouldn't be a point, that's more like a center, right? So you grow cells in exponentially increasing lengths around the center, right? So, and then you gather all the points that are close to the center with a grid of finer granularity, and as you go further out, the grid cells become coarser, right? And this actually works. So this gives you a corset of size k times epsilon to the minus d. Let's forget about what z and 1 and whatever, but so k times epsilon to the minus d times log n. Okay, this was the first corset construction. Okay, so how could we improve? I guess when you ask corset researchers, the term that they all want to get rid of first is not something that is bad in the exponent, in particular not bad. Exponential in D is maybe not considered as horrible as is a dependency on n, right? So it would be really good if we always got rid of any dependency on n first. And this is what Sayed Hapilet and his student, I forgot his first name, Kusha, thought to do as a follow-up to the first corset construction. And the solution was, well, let's not discretize by grid cells. We're going to discretize in a different way. They're just going to shoot out rays centered around the centers. And so these rays, it's basically an epsilon net of the unit Euclidean ball. The size is independent of n, of an epsilon net of the unit Euclidean ball. You snap all of the points to their respective rays. You can show that this moves the points by not too much, right? If I just project every point onto its closest ray. And what you do subsequently is just compute a corset in one dimension, right? Now every single ray is a one-dimensional object, and in one dimension it turns out that you can do many, many things fairly easily, and indeed you can also compute corsets. And by this corset of a corset property, this will then extend to the entire space. Okay. Good. So yes, so this was the first corset construction that was also independent of n, right? And fairly notable results. At the time, that was considered like a conjecture that you might need log n because, in streaming, we often had like log n type lower bounds. And but with fairly inexpensive, just a clever idea, fairly inexpensive techniques, you could already get rid of that. Okay, so this is kind of where I want to stop because the other geometric techniques that you can apply are complicated and they still are exponential in D, and this is what I kind of want to get away from. So just pointers. There is a very nice paper by Arya and Chan who showed, so essentially those foundational problems that the AHV paper proposed, they were all solved optimally in this paper. So if you're more into the geometric side of corsets, then read that first one. And the other one that I did want to mention, because it was surprising to me, and it was also nice to kind of see that there are still results like this out there. So there is actually a way to really utilize computational geometry to get something that sampling cannot. So if you're working in a low-dimensional setting, sampling will always induce an epsilon to the -2 error, and here you get actually something that is sublinear in epsilon in terms of your corset size.
So the first paper, does it consider epsilon kernel or something? The first paper?
Yes, the epsilon kernel, directional width, shape-fitting problems, all of that, yeah. Okay, so did they solve I don't know, like if they may have left out one or two, but most of them did, and I would be fairly confident that you could use their techniques for most of these shape-fitting problems, yes. Okay, so now we're going to move on to sampling-based approaches. And here there also exist two types of ways that you could sample. One is uniform sampling. So you just downsample the points, or like subsets of the points, but every time you execute sampling, it is done in a uniform way. And the other is sensitivity sampling, which was mentioned earlier today. The notion behind sensitivity is, we'll get to that in a moment, but basically I can gain a lot of power if I don't sample uniformly, but put more importance on certain points. Makes the analysis, of course, a little bit more complicated, but you gain a lot in return. Okay, so we'll first consider, okay, so why use one or the other? Generally, sensitivity sampling is always going to be better. However, there are sometimes reasons why we would want to use or have to use uniform sampling, because there are problems for which we just don't know how to analyze sensitivity sampling, but can analyze uniform sampling. There are problems for which sensitivity sampling, at least without additional pre-processing or post-processing or, additional ideas wouldn't work. One such example are capacitated clustering problems. But generally uniform sampling will always give you a worse result than what the sensitivity sampling analogs will give you. But it's still a good idea to start from the uniform sampling, if only to get a feel for your problem. So if you're unsure, there's there are reductions from uniform sampling to a Corset that are not too expensive. So if you feel like you're struggling to analyze sensitivity sampling and but think that you have something for uniform sampling, then you already have a result. Okay, so let's see why uniform sampling does not work. The 3 points on the bottom right, I won't pick them if I do uniform sampling, right? I'll only pick points from this big point mass on the top left. And this is a problem because the 3 points on the bottom right, at least if I stretch them out sufficiently far, so imagine that this distance is as long as I want to make it, they will dominate the cost. And if I cannot approximate my cost correctly, then of course I cannot prove that I have a Corset guarantee. So this theorem right here, it kind of sheds a little bit more light onto this impossibility statement that I just made. You need to ensure that the diameter, n times the diameter, is proportionate to the costs that the points are incurring. Here, n times the diameter is a factor of n larger than the cost, right? So that's why it didn't work. But if you can ensure that this here is constant, then you're in good shape. So this is what Chen in his seminal paper then set out to do. He imposed a pre-processing so that all the points have this property that they cost more or less the same. And with this, he could actually analyze uniform sampling. So the idea was you compute a constant factor approximate solution. There are variants of this. You can also take a bicriteria solution if you can get that faster. And at what constant factor exactly, that's just something that will appear in an oversampling parameter. So don't worry too much about how good or how many centers, just like a sufficiently good solution. You do this partitioning into exponentially increasing radii, right? So schematic, I know they're not exponentially increasing, but I hope the idea gets across. And now within every such ring, so between two successive radii, the points all cost the same, so this bad term that we looked at previously is going to be small, right? And then you can just say, okay, how many rings, how many times do I need to do the uniform sampling thing and then compute Corsets for that? That's going to be k log n because I have k such clusters. At least if you are computing a solution, it should probably consist of k clusters, and now the number of rings for every cluster is going to be log n. So you get kind of like k log n rings, so a Corset size of some poly k over epsilon times log n overall. Okay, so this was then later improved. So K-Chen basically gave me, if I have a Corset size for this nice ring case of size t, then you get a Corset for an arbitrary instance of size k log n times t. Again, we want to get rid of log n's first, right? So that's what happened first. With tremendous effort, you could replace log n with k times epsilon to the minus 1. With substantially less effort, you could have also replaced it with just epsilon to the minus 1. And I don't really encourage reading either of these two papers. So it's because nowadays you can do even better. So the main application for this, which I talked about this morning, was Corsets for uniform VC dimension. And yeah, here the takeaway message is that you don't even need the uniform sampling anymore. So this was kind of like the last the last important use case of uniform sampling for to get corsets for uniform VC dimension range spaces, and this is now also yeah, understood how to do that. Okay. So let's now move on to sensitivity sampling. So, and we're going to motivate this a little bit by considering this instance here, like why did uniform sampling fail exactly, and what could we have done about this? So we need to pick these, like at least one of these 3 points, right? If we don't, then we're not getting what we want. So uniform sampling cannot do that. So what if I just increase the sampling probability of these 3? And is there like maybe a systematic way of saying how much should I increase the probability that these three points should receive? Okay. So individually, they're a lot more important than all the points on the left, right? It's just that I have very few of them. So the way that we formalize this, or the importance score that these guys should receive, is by way of this notion called the sensitivity. It is possible that you've seen this in other fields under other names. So if you look at this in statistics, they call this leverage scores. If you are into graph sparsification, in particular spectral sparsification, this is what electrical resistances are for edges. So it's the same notion that's been rediscovered many times under many different names. It's a great idea, and yeah, therefore many different fields do come up with it. So what is this notion exactly? The sensitivity of a point that is the maximum impact that the point can have in any given candidate solution, right? So if there is a solution where the point completely dominates the cost, it's very important to keep this point. And this maximum impact, that's yeah, that is what I'm going to sample proportionate towards. Okay. So to just give you the idea, if we take like a miniature version of the instance from the slide before, these 2 points here, they would share, like they would have a sensitivity of 1/2 roughly, right? Because if I place this center here, then the impact that they both have is on the overall cost would be roughly 1/2. These points in this blob right here, they each have a sensitivity of 1/n roughly, right? Because they're like n points, and they're all they all contribute almost always the same in any given solution. Okay. So yeah.
So you mentioned that's related to active resistance as sensitivity score. What sense is it?
So yeah, okay, maybe I could.
It's not what we talk about.
Yeah, but I can actually say something about that. So if you imagine let's talk about cuts maybe for a moment. That's a little bit easier than we. So if I have a graph and I want to preserve cuts by way of a sampling distribution, and so like which cut intuitively is harder to approximate? It's not going to be a max cut or like a cut where you have many edges. A min cut or like a very small cardinality cut, those are harder to approximate. Right, so if I'm now saying, okay, this edge here appears in a very small cut, I want to sample that edge proportionate to the size of the smallest cut that will contain it, right? And yeah, this is also somehow, I mean, this is not exactly what electrical resistances are, but you're getting very close to that, right? So it's, I think a good way of thinking of it, it's always the impact that that the object that you're sampling has on the query that you're trying to evaluate. Okay. Good. So these sensitivity scores give rise to the following algorithm. I'm calling this an idealized algorithm because you cannot really implement it, or at least not for clustering you can. You can do it for certain other problems. So you're going to sample m points. M is the corset size that you can prove, at least, yeah, that you get an upper bound for. Points independently and proportionately with replacement to the sensitivity. And then you weigh each point inverse to its sampling probability. So the reason why you cannot, for some problems, like regression, or indeed electrical resistance. You can't compute the sensitivities exactly, right? Maybe there's an issue of running time. If you want to use it to get a very fast algorithm, you should maybe not compute them exactly, but you can. There exist ways to actually obtain the sensitivities within like machine precision parameters. For clustering, this isn't really the case. So you can imagine this kind of, it feels almost as hard, or like should be as hard as solving the problem optimally. And it's actually a little bit harder than even that, right? So you shouldn't expect to get the sensitivities exactly, but you can compute approximations thereof, right? So yeah, this idealized algorithm you're not able to implement, but you are able to implement algorithms that are fairly close to this idealized thing. Okay. And since this was supposed to be a tutorial, I'm now going to analyze this idealized algorithm, so show how we can use the sensitivities to get fairly good bounds on the Corset size. Okay. How do we proceed? First, we show that any arbitrary solution is going to be well approximated by our sample. And then we would show that the cost of all solutions is going to be well approximated. I'm saying we would because the first step that I'm going to show you today, that's very general, so that will always hold. The second step depends on the metric and the problem that you're currently considering. Okay. Right. So the Corset that we're constructing, in a sense, it's a random variable, right? It's a randomly selected point set that is somehow weighted. So it's a random variable, and the first few things that you could ask of a random variable is what is the expectation? So let's take a look at the expectation first. And this will also give you some insight as to why I'm weighing them the way that yeah. Okay, so if I take a look at the expectation of a single point sample proportionate to the sensitivity, right? Let's never mind that we have maybe multiple points. Just take a look at the expectation of a single point. So the weight of this point, that was 1 over the probability by which I was picking it. And if you now evaluate this expectation, so you sum up every one, right? Then the probability of a point appearing is, well, it's of course the probability of a point being picked, so these two cancel out. So it turns out that if I am weighing the points inversely proportional to the sampling probability, I always get an unbiased estimator, right? So this is already good news. If I'm using a random quantity to estimate another quantity, it's a very good idea if it is on expectation estimating the right thing. What we have to still argue is that it's concentrated. And just looking at the expectation, it won't give you too much because I haven't really used anything about my probability distribution here. So this trick of canceling out the probability of being picked with the weight, that will hold for any distribution, right? So the important parts of sensitivity are yet to come. Okay. So the way that you now, improve the concentration of an estimator is usually by repeating the experiment a few times and averaging over it, right? This is what we're all told in a basic statistics course, right? You have some unbiased estimator, and now just repeat the estimate a few times, and hopefully it will get closer. I mean, it should always get closer to what you're trying to estimate. Okay, so how do we measure this? Well, between these two distributions that are trying to estimate the same thing, right, we know that the red one is better because it's a lot more concentrated, right? This blue one has like a lot more mass spread out in parts that I don't want. This red one is a lot more concentrated, and the way that we can, I mean, these are like Gaussian distributions that I plotted. The way that we can measure concentration of a Gaussian, or that's the primary measure of concentration for a Gaussian, is variance, and this is indeed what we're going to look at now. Okay, so variance is, like if you just write it down in terms of expectation, it's the expected second moment that you center around the mean. And if you can now show that, or if you want to apply, let's say, a simple concentration inequality like Chebyshev, then the probability that you'll be within a 1 plus epsilon approximation of the value that you're trying to estimate, that is this probability. So let's say we want that probability to be like, or that you're not estimating it correctly, I should say, that is this probability. So if we want a failure probability to be no larger than, let's say, 1/3 or something, I just set this term here to be 1/3, and then I try to say, okay, like how much do I have to decrease the variance of my estimator in order for this to have worked for an arbitrary solution. Okay, so what you can prove, this is the correct answer, is that the sensitivity, that the variance of the sensitivity estimator is of the order k over m times the cost of the solution that you're trying to estimate. So the important thing is here this k, right? That's the one parameter that I have to pay for. So this is definitely true in like a worst case setting. It's not true for all solutions simultaneously. So there are solutions that, of course, you'll need less random samples for, but you can show that in general this bound here is tight. Okay. So now let me actually show how we can. I'll give you a weaker bound on the variance, right? It's a little bit simpler to prove. And here we can also see how the sensitivity came into, like how we're utilizing the sensitivity. So the sensitivity was defined like this. So it was the maximum impact that a point could have. And now for any given candidate solution, right, this sensitivity is of course going to be an upper bound for the contribution in that particular solution, right? Because the sensitivity is a supremum over all solutions. If I consider any fixed solution, that can only do worse. Okay, this large sigma here, that's what's known as the total sensitivity. We'll see that this value is going to be important in just a moment. And now let's consider how we can reformulate this term from before in terms of this, this total sensitivity right here. So the probability of picking a point, that is proportionate to the sensitivity, meaning you take the sensitivity of the point and you divide it by this total sensitivity thing here, right? That is the probability by which we're picking a point. So 1 over that probability is just the total sensitivity but divided by the sensitivity of that point. Okay, now we cash in by applying this inequality here, right? So the sensitivity of p, that was at least as much as the cost of p divided by the cost of the solution that we're currently trying to estimate. So I can just plug that in, right? And this now cancels out, so I'm left with the total sensitivity times the cost of the solution. And this is exactly what I wanted. Okay. So if you now are looking at the variance, you are just looking at, you can upper bound that by the second moment. This is where I'm going to be a little bit looser. This is not tight. But yeah, I'm just going to upper bound it by the second moment, so I get to plug this in, and then you get the total sensitivity squared times the cost squared. Okay. So this holds in general, right? For any function that you're trying to approximate, whenever you're trying to use sensitivity sampling, this will always hold. I haven't used anything specific about k-means or k-median. What you can show for k-means and k-median is that the sensitivity is of the order k. Right? So what we've now managed to prove in a fairly inexpensive way is a variance bound of k squared. And you can actually do k. Okay. Good. So now we're going to go to the second stage of the Corset analysis, which is what I like to call the union bound stage, where we're trying to extend this to all possible solutions. So if I can show that with very good probability I'm approximating the cost for any arbitrary but fixed solution, how may I now show that this now applies to all solutions? Well, in a fairly straightforward way, if I have at most t solutions, I'm going to define a failure event for any particular solution, let that be fi. And this here is now the union bound, so the probability that you fail overall, that's the union of all of these failure events, you can upper bound that by the sum of the probability that you're failing for any given one. And now I can write, okay, this fails with at most probability e to the minus delta, right? And the number of solutions that I'm summing over is t. So you get this bound here. So if I just want a constant success probability, I now just have to solve this for the success probability that I want. Okay. Right. So let's see a very simple way to conclude a Corset proof. So if you have a finite endpoint metric, meaning that my input just consists of endpoints and I can place centers on any one of these endpoints. Then you have at most n choose k many ways of placing centers on these points. That's roughly n to the power of k. So your t is of the order of n to the k. So if you just now plug this in with the variance bound that I claimed, the variance bound that I proved, that was k, so this would be a k to the 3. Then you just get epsilon to the minus 2 times k times log of the number of the solutions. And this gives you Corset size, so epsilon to the minus 2 k squared times log n. Right? So for finite metrics, it's actually fairly, I would say mild to analyze this. The complicated part, of course, happens if the number of solutions that you're considering are infinite. And we'll get to that in a moment. Okay, so this here now is as good as you can do it in finite metrics, right? You can actually show that k times epsilon to the minus 2 times log n is the right answer. And for finite metrics where I'm giving you a little bit more information, such as bounded doubling dimension or whatnot, you can also improve this bound. So the log n isn't important. You can also get something a little bit better in terms of the doubling dimension. And these bounds here are tight. Okay, so the, I guess, more challenging part now is if you cannot easily enumerate over all solutions, right? So finite metrics, that's really, I like starting with that because it is easy, but it's a false friend, right? In general, doing this union bound stage is very challenging. And I guess the holy grail of Corset research, at least for clustering, is, well, how can you get the best possible enumeration for Euclidean space, right? And this is what this is now what I'm going to, in the final few minutes, talk a little bit about. So what you want to do, if I'm now, let's say, placing a center right here, I mean, there are, of course, infinitely many centers to place, right? So first off, just enumerating over everything, that won't work, right? No matter how small my failure probability is, I cannot kill infinity in that sum, right? So I have to do something smarter. And the way I do this is I impose a discretization, and you can actually think of this discretization as being fairly similar to these geometric decompositions that we saw earlier. So I impose a discretization over my point, over my space. And now instead of trying to perform a union bound over this particular point right here, I will now just snap the solution to the nearest point in my discretization. And if the discretization satisfies this property, that for every point that I'm considering, the cost, the difference in the cost is fairly small, then you can actually show that it is sufficient to only prove a union bound over this. And I made my infinity finite. And what's more is the granularity of this discretization you can actually get from computational geometry. So those older Corset results, you can even imagine that they're something like, that they're more useful as a discretization result for Corsets rather than Corsets themselves, right? So that's where they still really have relevance. So if I'm doing this for a single center and I use these old results by Harpelet and his students, you would get a discretization of this order, right? So it's epsilon to the minus b, but since we're taking a logarithm, I'm just raising it to the power right immediately. And for k solutions, right, then I just need to select more centers from my discretization. So then I'm just getting a k in there. Okay, so if I just do it this way, then I'm still going to get I'm still going to lose a factor of d. And the way that you now improve, and this is what a lot of work has gone into, finding the best possible dimension reduction that somehow preserves Corset guarantees or preserves cluster guarantees, and try to do a union bound with those. Here I wasn't quite sure if David would talk about this because he did indeed also work on this, so I steered away. I limited myself to just giving you an outlook of all the work that went into this. So it's a little bit like what Amit said. If I put everything that has been done here in very small fonts, I would fill multiple slides. So it's just like a selection of the results. So I just want to highlight a few. This result right here, this was the first one to get rid of the dimension entirely, right? This here was the first one to get something linear in K. So the older dimension reduction results that were based on linear algebra, they would basically replace a D with K. So it wasn't really clear how to get below K squared. And yeah, the state of the art are these two results, K times epsilon to the minus 4 and K to the 1.5 times epsilon to the minus 2. I was so sure that that the right answer had to be K times epsilon to the minus 2, right? Because, yeah, if anything, it says like linear in K is possible, epsilon to the minus 2 is possible. So I was a creature of faith, and I strongly believed and spent so much time trying to prove K times epsilon to the minus 2, but surprise, surprise, this was already optimal. So this very weird bound, K times epsilon to the minus 2 times either the minimum of epsilon to the minus 2, so that would be this bound, or square root of K, those bounds are optimal. You cannot do better. Okay, good. So I think that is all that I had to say. So thank you for sticking it out. And yeah, if you have any questions.